Before we can multiply matrices together, we need to understand the dimensions of a matrix. True to their name, columns are straight up and down. As we see here on the matrix, A and C form a column, and so do B and D. Likewise, rows are horizontal, or across. In this case, A and B form a row, and C and D form a row. When we describe the shape of this matrix here, we will say this is a 2 by 2 matrix, or this represents the number of rows, and this is the number of columns. There's an infinite number of possibilities when it comes to the matrix shape, but it will be really important when we start multiplying them together. Adding two matrices together is fairly straightforward, but they have to have the same dimension. For example, you couldn't add these two matrices together because this one has 2 rows and 2 columns, but this one has 2 rows and only 1 column. These would be impossible to add, since these two dimensions are not equal. Instead, a 2 by 2 matrix can only be added to another 2 by 2 matrix, like so. It's impossible to change dimension when adding two matrices together. For instance, if we start with a 2 by 2 matrix, you will end up with a 2 by 2 matrix. Addition is performed term-wise, meaning the top left term of the first matrix is added to the top left term of the second matrix, resulting in 2 in this case. The same is true for each of the other terms, where they're added to their respective positions. Let's write this in a more general form to get the idea across. Let's pick a different matrix shape this time. How about a 3 by 1? Each of the positions will be filled with a letter to represent an arbitrary number. Recall from last time that 3 by 1 matrices can only be added to other 3 by 1 matrices. The resulting matrix is also a 3 by 1. Just like last time, the addition adds each term to its respective counterpart. A is added to D, B is added to E, and C is added to F. Now that we have a sense of matrix addition, let's move on to multiplication, which is a significantly harder process. When talking about matrix multiplication, let's start off with an arbitrarily sized matrix. Let's call it M by N, where these just represent some number of rows and columns. This is where it gets a little tricky. A matrix can only be multiplied by another matrix that has the same number of rows as this first matrix has columns. This M by N matrix can only be multiplied by an N by something matrix. In other words, the number of rows in the second matrix has to equal the number of columns from the first matrix. For instance, we could have an N by 1 matrix over here. The resulting matrix will have a combination of the other two matrices' dimensions. It will be an M by 1 matrix. Another way to think about this is the two inside terms cancel and are left with M by 1. Let's see this in practice. Let's say that my first matrix here is a 2 by 3. 2 rows, 3 columns. This means that the second matrix here will have to have 3 rows. It can have any number of columns, but let's let it be 1. The resulting matrix will be the leftover dimensions once these 3's cancel. In other words, it is a 2 by 1. Now, what are the numbers that should go here in our 2 by 1 matrix? Well, this is why matrix multiplication is tricky. We would have to take the row of the first matrix here and dot it with the column of the second matrix. In other words, the first term of this row is multiplied by the first term of this column. That is then added to the second term of this row multiplied by the second term of this column. Lastly, that is added to the product of the two last terms of the third term of the row and the third term of the column. What we will end up with is 1 times 7 plus 2 times 8 plus 3 times 9. In other words, 7 plus 16 plus 27, for a total of 50. The same process will repeat for the second row of this column. 4 is multiplied by 7, added to 5 multiplied by 8, added to 6 multiplied by 9. Therefore, in this spot, we will have 4 times 7, or 28, plus 5 times 8, or 40, plus 6 times 9, or 72. This leaves us with a total of 140. Therefore, the entries in our 2 by 1 matrix are 50 and 140. Let's create a general picture of matrix multiplication using a 2D example. In this example, we have a 2 by 2 matrix multiplied by another 2 by 2 matrix. Therefore, our resulting matrix will also be a 2 by 2, since if we cancel out these middle two dimensions, the outside dimensions are still 2 by 2. Let's consider the top left entry of this 2 by 2 matrix first. In order to calculate its value, we have to take the first row of the first matrix and multiply it by the first column of the second matrix. This will result in A times E plus b times g, as seen here. The top right entry is on the first row in the second column. Therefore, in order to calculate its value, we take the first row of the first matrix and multiply it by the second column of the second matrix. This will result in A times F plus B times H, as seen here. This bottom left entry is on the second row but the first column. Therefore, we will multiply the second row of the first matrix by the first column of the second matrix. This will give us C times E plus D times G, as seen here. This last entry is the second row in the second column. Therefore, the second row of the first matrix by the second column of the second matrix will give us C times F plus D times H, as seen here. As a recap when multiplying matrices together, make sure that the dimensions line up. In this case, we have 2 rows and 4 columns, so this is a 2 by 4 matrix. Next, we have 4 rows and 2 columns. Therefore, this is a 4 by 2 matrix. Our result, 2 rows, 2 columns, is a 2 by 2 matrix. See that when I cancel out the 4's, the dimensions I left with are 2 and 2. If I wanted to find the entry in the X row and the Y column, I would have to select the X row on the first matrix and the Y column on the second matrix. In this case, it is the first row and first column. With this row and column selected, multiply the respective terms and add their products together. This will give you the entry in your matrix. I know this concept can be kind of confusing, but the more you practice it, the better it is. I would suggest trying working with matrices at different dimensions to get a feel for what happens when you multiply them together. Fortunately, a lot of linear algebra uses square matrices, but every once in a while you end up with an example like this. Keep working on it and eventually get the hang of it. I hope that makes sense, and thank you very much.